Welcome everyone for what is the third event in our Encode Tezos series. Today we're going to go a little bit more technical. Look, we've had an overall introduction to blockchain, which I gave, I think now 2 weeks ago. Then we did a kind of dive into Tezos, just in general respect, that I also gave last week. And now we're going to go for a kind of more technical overview, which is probably more focused on the technical folk, quite frankly, but hopefully should still stay be broadly relevant if you're not super technical. But this will be more aimed at technical folk to get you start thinking about building great things on Tezos. This event is recorded and will go online tomorrow. Alongside the slides that will be presented. Vanessa from our team is going to drop in various links about Encode, about the program. It's never too late to take part. These events are marketed on an individual basis, so you can bring friends in for future ones, or afterwards we'll be doing a hackathon and an accelerator. So there's lots of great things to come, but I'm really delighted to introduce our two speakers today from the Tezos side. We've got Dani, who's one of the blockchain experts at TZ Connect, and also John, who is technical director at TZ Connect, and they are quite frankly fantastic, and you're in very capable hands this afternoon, evening, or morning in my case, wherever you are. Without further delay, Dani, John, thank you very much for being with us today, and I hand over to you. So please do tell us everything about Tezos. Last thing, guys, if you have questions, chat is our friend, so please do put them into chat, and we'll get to them throughout the event. Over to you guys.
Yeah, sure. So we're going to start with some slides and a discussion of kind of the relevant points of Tezos for developers, and introduce some SDKs, some contract programming languages, some command line utilities, and the process of deploying a contract onto the Tezos network. And then we are going to show how to set up an account with Tez from the faucet for the testnet, and to install the tools, deploy and contract, and hopefully to mint some tokens, just so that you can get an overview of all of the steps involved and see all of this. And then afterwards, if we have some time, there will be questions, or just ask questions as they occur to you, and we will answer them as we see them. Over to Dani.
Hello, so I'm Jozsef. I work with TZ Connect as a blockchain expert. I work quite closely with John. I'm going to be talking mostly about the theory today, and John will do some demonstrations. We're going to be giving you an introduction to the technical stack of Tezos and smart contract development in Tezos, and how to connect and get started with Tezos in general. We'll go through a few tools. So there have been already two classes where we went pretty deep into blockchain topics, and the second one was about Tezos specifically. So now just a little recap. So the Tezos is a public blockchain. Its native token is called Tez. And unlike Bitcoin or currently Ethereum, Tezos is a proof of stake blockchain, which means that validating blocks is not done via expanding computational power, that is so-called mining, but by a collaborative process where people stake or put up as collateral their cryptocurrency, their Tez that they hold, as an incentive to stay honest and validate the blocks correctly. And the version of proof of stake that Tezos uses is called liquid proof of stake, which means that the baker status, the baker is what we are calling validators in Tezos land. So the baker status is permissionless. There is no specific allow list of validators like in some delegated proof of stake blockchains. But you need to hold at least 8,000 Tez in order to stake, which is a few tens of thousands of dollars at current valuation. And people who do not have that amount of Tez, or just do not want to validate, because validating means you need to run a computer 24/7 that needs to be reliably connected to the chain. They can delegate their holdings to bakers and earn some sort of income from that. One of the key features of Tezos is on-chain governance, which means there are regular votes that happen on-chain about the future of Tezos, and this means that that the Tezos blockchain regularly upgrades its own protocol through this governance process. So about every 3 months, a new protocol gets rolled out on Tezos, which allows for a very smooth and continuous development roadmap. The reference implementation of the Tezos node is called Octez, which was built in OCaml. OCaml is a very old functional language, and this shows that Tezos has a very strong functional programming culture. So most of the people who started designing Tezos and worked on Tezos in the early days were functional programmers. Tezos, like Ethereum, has contract accounts and accounts that are connected to wallets. Smart contract accounts are in Tezos, as in Ethereum, are governed by code, but Tezos is not an EVM chain. So it has its own virtual machine called the Michelson VM, which is a strongly typed stack-based virtual machine. And the way the Michelson VM is structured, and the strongly typed characteristics, as well as the specifics of the Michelson language, make it much easier to formally verify the various claims about a Tezos smart contract, much more so than an EVM or a WASM smart contract. Contracts are strongly typed, so this means that for each contract, we have a storage type and a type of call parameters that is like what you can call it with, and this is quite visible and very fundamental to how Tezos operates. The prefix of a contract address in Tezos is KT1, so it would be KT1, and after that the hexadecimal base 58 address. Then the accounts connected to a signing key, that is to a wallet, are called in Tezos land implicit accounts. And Tezos supports multiple signing algorithms. So currently 3 elliptic curves are supported. There is TZ ED25519, SECP 256K1, and the NIST B256. And these are identified by the TZ1, TZ2, and TZ3 prefixes. And as you can see, this means that eventually maybe TZ4, TZ5, etc. could be added as potentially KT2, KT3, meaning potentially other virtual machines. So Tezos was designed from the ground up to be quite extensible. Implicit accounts are in Tezos, implicit accounts are also treated as smart contracts. Smart contracts with a code that does not do anything, and they have the storage type and call parameter type of unit, which is the empty type. So it's like, here's something and it has nothing in it. So when you call, when you transfer Tez to a wallet address, an implicit address, you cannot add any like message to it or something like that. There are like ways to go around if you need that functionality. Tezos has a 30-second block time, but that is subject to change. It has changed in the past, and it might change in the future with protocol updates. Blocks and transactions are constrained both by size, that is how many bytes they are, and by gas, which measures the amount of computational time that executing them costs. In Tezos, transactions are badged by default. So for people who might be familiar with Ethereum, they would know that on Ethereum, transactions cannot be badged by default. So you need to have, like, for example, a smart contract that would execute a number of transactions in a batch so that they would be atomic. In Tezos, this is part of the protocol. So you can execute multiple operations as an atomic unit so that all of them succeed or all of them fail at the same time. And Tezos, when you execute something, of course, you need to pay a transaction fee. And the way this fee is structured is that there is like the actual transaction fee that the baker gets who bakes the block, which is made up of a minimum fee, which is a function of the size and gas cost of your call, and some tip above that you decide. And also you have to pay the network, that is all of the people who hold Tez, by burning a certain amount of Tez as a storage fee. So since like the storage on chain is a public good, or it's considered a public good, by creating a deflationary pressure, you are rewarding the people who hold Tez by burning Tez. We're going to talk about multiple Tezos components. We'll talk about the node, that is the Octaz implementation of Tezos, and the Tezos client, command line client that comes with it. We'll talk about smart contract languages, specifically CameLIGO and SmartPy. We'll talk about two popular libraries that are used to access Tezos, Taquito, which is a JavaScript, TypeScript library, and PyTezos, which is Python. And we'll talk about the token standards, FA 1.2 and FA2 in Tezos, about NFTs, and about, in general, like some thoughts on how to go about developing something for Tezos. John, would you like to take over from here?
I certainly would. So the Tezos node is relatively easy to run in contrast with Ethereum and Bitcoin nodes, which can bring the strongest machine to their knees. Until recently, it was true that you could run a Tezos node on a Raspberry Pi, but with the increasing use of the blockchain and the increasing tasks that the node provides, this is probably still just about possible, but honestly, one would not do it in practice. Various people offer public nodes. We put a list in the repository for this presentation. This is changing quite fast, I think, but unfortunately at the moment, there isn't really a commercial public infrastructure for Tezos where you get a service level agreement and you pay a subscription and things work faster than with the free ones. Occasionally you find that a public node will go away, which can be quite annoying, but broadly it's quite easy to get onto the Tezos blockchain, and we will demonstrate this later. Another big difference with Ethereum and with most other blockchains is that Tezos doesn't have long-lived testnets because the protocols upgrade so rapidly, so frequently, and because there are voting cycles in the protocol, there's a risk if we had a long-lived testnet that the people who voted on it would make different decisions than the ones who voted on the mainnet, and the testnet would then diverge. So what we currently do is to set up a new testnet every time there's an upcoming protocol version, which one can use when working out what to do with the next one. There's one for the current version. And then there are the carcasses of various old test nets which gradually die of disinterest because nobody really cares about them anymore. New protocol versions come along approximately every 3 months. In the protocol, the maximum rate that they could be introduced at is every 3 months. But due to the messy nature of democracy, sometimes protocols are proposed and voted down, and then another proposal is produced, and that might be voted down too, and then ultimately one succeeds. So if they went regularly as fast as they could, it would be every 3 months. I think the gap between the current and the next will end up being about 4 months, but really quite frequently. In addition to using the public blockchain nodes, there is a really useful tool known as FlexTezer, which will run a local test chain, which you can use for developer testing. You set it up, you get some funded accounts, and you can tell it to bake as fast as you want. So for automated testing, this is a really valuable resource. And again, the links are in the notes to this presentation.
The Tezos node exposes its functionality through an HTTPI API. Now, unlike the Ethereum nodes, which some people might be familiar with, this does not use the JSON RPC protocol. So even though it is an RPC and it does use JSON, it is not JSON RPC. It is plain HTTP with HTTP URLs that you can call with a JSON parameter and you get something back. There is the ability that when you're setting up a node to configure what parts of the API will be accessible on that node, and you can restrict access to certain parts by IP address and other filtering. There is a command line client called Tezos client, which comes with the node implementation. This is a command line tool for interacting with Tezos. It exposes the full RPC API to a command line in a relatively friendly format, but still it can be a bit fiddly, especially with escaping characters. So when you need to input something with lots of brackets and spaces, it can be a bit uncomfortable in Shell. But often this is the most straightforward and simplest and quickest way to do something simple on the chain. And it also supports Ledger hardware wallets. So if you want to do something with a Ledger hardware wallet key quickly and you know exactly what you need to run, Tezos client lets you do that.
Of course, working on the mainnet involves spending actual TES and involves a certain amount of visibility, which is not going to be right for your project before you are ready to unleash it upon the world. And so you will be wanting to use a Tezos testnet. As I said before, there's a new one for every Tezos protocol upgrade. They don't live very long. And of course, because the testnet starts from zero, it's extremely easy to run a local node. I love running nodes. I think it's fun to do it, and you can really see how the Tezos software is built, and you get a sense for the philosophy of it. So I do recommend that anyone who's got any desire to geek out a little bit, just set up a tiny little box somewhere on the internet and join a testnet. It gives you exposure to running blockchain nodes, and it's extremely inexpensive and, well, really quite good fun. To onboard onto a testnet, you might find a public node. There's a list of them out there on the internet and one in our repo, of course, or set up your local node and get it synced onto an active testnet. There is a faucet at testnets.xyz, which will give you testnet TES. There used to be one faucet for everything, and as time went by, the number of TES you got from it went down and down and down, which was a little bit depressing. So at some point they reset, and now every testnet has its own faucet, which means that when we take our TES from the faucet, we may have 100,000 of them, which is obviously great. To be rich on a testnet is fine, although it's meaningless. And all of the tools that you use need to be pointed at the testnet node. So you have to configure that they're going to access this node.
When you're coding on smart contracts or thinking about smart contracts on Tezos, one of the most important things about or differences from some other chains is the Michelson VM, which was one of the core features of Tezos with its strongly typed, verifiable nature. So this is a strongly typed stack-based VM, stack-based in the sense that the operations operate on a stack of typed objects. So unlike a hardware stack where you put in like words of bytes, here this stack is can be better imagined as a stack of pointers. So you have like logical objects of any complexity or size occupying a single space in the stack. And there are operations in the Michelson language that can unpack or pack complex types. So for example, like take the left half or take the right half of a tree and operations like that. Michelson also has functional features. So lambdas are an atomic type. of course, it's a parametric type because it's a strongly typed language. So each lambda has input and output types defined, and only the full type with everything defined counts as equal to itself and not any lambda to another. So when you, for example, when you define a container for a lambda, you need to say what kind of lambda it will be. Smart contracts in Tezos, as I already mentioned, are defined by the type of their storage. So the storage is the state of the smart contract that is saved onto the blockchain between executions. So for example, if you have a very simple like toy contract that adds numbers to like a running total, then the running total would be the storage of the smart contract. Then there's the call parameter type, which is the type that the smart contract can be called with. And this is one single type, but it can be of like arbitrary complexity. And with like this complexity is that we will achieve multiple functions that can be called in a contract. We'll talk about that a bit later. And the code of the smart contract is a pure function in like functional programming terms, which means it does not have any side effects. It takes an input, transforms it, and outputs an output and doesn't do anything else. The input of a smart contract called in Tezos is the storage type and the call parameter type together. So when you call a smart contract with a call parameter, then it gets as its input the current storage and your parameter, and it will output the new storage and a list of operations, which we will talk about in a bit. So when we get back to this simple contract that keeps a rolling sum, the way it would work is, say the current sum is 10, and I call it with 5, then the code would be called with 5 and 10, and return 15. And the blockchain automatically writes 15 down as the new storage. When we're calling a smart contract on Tezos, we do that with the chain operation called transaction. This may transfer Tez, and this is the same operation that we use to transfer Tez between implicit accounts, that is wallet accounts. A transaction operation includes a call parameter. If we're transferring some Tez to an implicit account, this has to be of unit type, that is the empty type. But when we're calling a smart contract, then it needs to be the type of the smart contract call parameter. And here we get to entry points, which is Tezos is a solution to having a smart contract expose multiple functions. So the call parameter of the smart contract can be of a union type or an option type, which can be like it's a way of defining a type as it can be this or this. So for example, with the rolling total smart contract, we can go further into like, okay, so now we also want to be able to subtract from the rolling total. So now we have add and subtract net, which means we would be subtracting a natural number. And these options can even be nested. So you can have like a structure which has all the admin operations, and that is like all grouped under an admin leaf of so node of the tree. So you can have like a sort of a tree of operations. And Tezos offers a shorthand when a smart contract's call parameter looks like this. And this way we can like quickly call any uniquely named option of these as an entry point. So the way that we would notate that is like percentage mark add and 12 n is it just shows that it's a natural number and not an integer in Michelson. And this way Tezos would know that you are wanting to call this smart contract with that specific type of input. And of course, the add functionality would run. Another strangeness in Tezos is something that was introduced as a way to make formal verification easier, and that is contract interoperation is asynchronous. So when if someone comes from Ethereum, there you can call other contracts synchronously. So your code flow just going, and then you say, oh, I need like a balance from this other contract, and you call it, and your code will just continue on from there. Not on Tezos. On Tezos, first your whole code runs, and then it can return this group of operations, this list of operations that I mentioned before. And these operations are things that you want to happen after your code has run. And these may include contract calls. Now, in the last protocol update, they included on-chain views, which allow a simpler and synchronous way of querying the state of other contracts, but not like running any modifying or write operations on them. But yeah, before this update, it was like really complicated to even query the state of other smart contracts.
This is a little bit of a side tour, just a question of when we're going to be writing smart contracts or code that accesses them, what are we going to put on the blockchain and what are we going to have running in our application code? Because every node has to have all of the storage of the blockchain, it's extremely expensive to store data there. I believe this number's wrong. I think it's a little bit cheaper now, but it's still quite an eye-watering sum. It was 0.01 Tez per byte, which was about $2,000 per megabyte. Sometimes it's illegal to put blockchain data on. Blockchain data is available to anyone who looks at the nodes, so you absolutely shouldn't put anything there you would not be happy with the whole world reading. And in fact, especially in Europe, it can be illegal to put this data on the blockchain. Not only should we not put data on, we also have to be very careful when we put the hash of data on, because other people can just cycle through everything they think it might be. And if they hit our hash, then they know that it's there. So ciphertext or sensitive data is also sensitive data. So the answer to it is not to keep too much data on the blockchain, to put it on your own server or on IPFS, and to generate a salted hash from the data. So put some number into the hash so that just running loads of queries on the hash will not reveal whether it's your data. And then you can put this onto the chain as a proof of existence of the data. In the case of NFTs, we put the NFT in IPFS typically, and then we put the IPFS hash onto the blockchain. And even though we just store an IPFS hash, storing that hash is still the most expensive part of the transaction, which records the ownership of an NFT, which mints an NFT. The philosophical take home here is that the blockchain just records transactionality. It stores ownership records. It does not store the thing which is owned. And we have another digression of what belongs on chain. So we don't want to store data on chain, but we also don't want to do very much computation on chain. Mr. Arthur Brightman came up with this great line: if 100 lines of code off chain can save 1 line of code on chain, I would consider that a good trade-off. It's expensive to run stuff on the chain because it runs everywhere. It's expensive and it's slow and it's very difficult to change. So, I mean, I'm a terrible programmer and I've got used over the years to the fact that I can write terrible code and then fix it in production or when a problem arises. This is not possible on the blockchain. And I think we've all seen enough news stories about eye-watering sums of money being lost or stolen that we can understand the consequences of that. So designing a distributed application involves finding exactly the minimum that you can do on the chain while retaining trust characteristics, and just doing that and putting the other logic somewhere where it can run more cheaply and where it can be fixed if it needs to be fixed. And another take home is that a smart contract shouldn't try to do the job of an indexer. So there are programs which index the blockchain and make the information easily accessible. Your contract does not need to do this. It should never be searching through maps looking for a particular key. It should never be dealing with lists and iterating over them. That stuff can also happen off the blockchain.
Okay, so I'll talk a bit about Michelson. So Michelson is theoretically human readable. And in the early Tezos, it was used as the preferred way of coding because there were no higher level languages yet. And it can be used. Like I have done some Michelson coding for like fun, As long as the smart contract is really, really simple, it's quite doable. And in a way, it's entertaining, similar to coding an assembly or something. But if you want to do anything complex by hand in Michelson, you're going to be really frustrated. So I think in general, no one here is going to be coding a whole lot of Michelson. But I do think we should strive to be conversant in it, to know all the opcodes in Michelson and know like what really our high-level codes compiles to, because it just makes debugging and understanding the implications of the things we do on chain so much easier. Here, this link leads to a reference document. It just shows all the types and all the operations available in the current version of Michelson. Um, I think it's a really good thing to peruse at times. And these 3 lines, this is an empty contract written in Michelson. Like this doesn't do anything. Um, as it says parameter unit, that means the call parameter of the contract is unit, which is the empty type. Storage unit, that means the storage of the contract is the empty type. And then the code is this thing. So coder comes from Lisp. It means take the right half of the pair that's currently on the top of the stack. So now after running this, so when we call the contract, of course, as we said, it is called with the parameter and the storage. So we have a tuple of parameter storage. So after coder, storage will be on the top because we only took the right half. Then when we say nil operation, that means we insert an empty list of operations, that is of the type operation, at the top of the stack. So now the stack has 2 things. It has an empty list of operation and the old storage, which is empty type. And then pair means to take the top 2 entries on the stack and combine them into a tuple. And of course, the top of the stack after ending the run is the return value, which is the storage type and a list of operations, which is exactly what we want out of this. So as you can see, it's understandable. One can reason about it. But once we're talking about like records of like 15 entries, so for example, like when we're talking about DeFi or something, it just becomes completely unreadable.
So, full disclosure, CameLIGO is our favorite of the smart contract programming languages, and we will not attempt to hide that. It's a member of a family of languages called LIGO. There are different front ends to the compiler, which resemble Pascal, which resemble JavaScript, which resemble ReasonML, but CameLIGO is the OG of the LIGO family. And we find that it fits the best. It's a high-level language with functional elements, which compiles to Michelson. It offers good code optimization and increasingly good error handling. And it now has some really quite nice tools to help you with unit testing. So it has a Michelson interpreter inside the compiler, which will run your code and run unit tests for you without you having to touch a node. The CameLIGO syntax is based on ML, which is a venerable language. It's been around, I guess, 40, 50 years. The syntax looks a bit odd when you first encounter it, but one gets used to it very quickly, and it tends to push one in the direction of writing relatively good code. The fact that it looks like OCaml, which is the node's native language, is probably related to the fact that it's the most mature of the Legos. It's a natural fit for Tezos programming, in our opinion, to use an ML family. And lastly, but actually not leastly, the compiler produces the best optimized code of the Tezos smart contract programming languages. So your contract will run more cheaply, which is always a plus.
Okay, SmartPy. So SmartPy is probably the most popular smart contract language currently on Tezos, which it probably owes to the fact that everyone knows Python these days. SmartPy is implemented as a Python library, so it's not a separate tool. It's something you include in your Python code. And it is a meta-programming language, which means that it's not like we are running a compiler with our code as its input, but we're running the Python code itself that we wrote, and it outputs Michelson code. The Python flow control structures are executed at compile time, and then there are these special flow control structures which say what flow control I want in my Michelson. So what will happen during contract execution. This can be a little bit confusing, but there are very good tutorials, and SmartPy is relatively good at hiding this this fact at like more simple tasks. SmartPy has its own Michelson VM, which means it's very fast and easy to do unit testing in it. Now, the quality and up-to-dateness of SmartPy's Michelson VM has been contested at times, but it's still considered relatively good. And it, of course, since it is the most popular smart contract language on Tezos, it has amazing community support. So if you run into something with coding SmartPy, there will be like a lot of people who can help you. Now, this is a personal digression, but we don't really prefer SmartPy because so Python is weakly typed and Michelson is strongly typed, which means there's this like friction at the two things meeting, and it just becomes a little bit overcomplicated because of that. And it would seem that the optimization that SmartPy offers in terms of the length and efficiency of the Michelson code it outputs is not as good as what the CameLIGO compiler generates. Now, this may be a controversial opinion. Some SmartPy aficionados might say that we're just using it wrong. But our personal experience was that CameLIGO resulted in better code for us. John, would you like to switch over to the demo then?
Okay, this is the first time I've attempted this, so it may very well go wrong. But it's just an attempt to show how to set up a machine with all that you need to compile smart contracts and put them onto the testnet. And we're also going to attempt to mint an FA2 NFT during this presentation. So there's actually a setting up Ubuntu document on our GitHub, which we'll point you at. And the first thing to do is just to install all of the prerequisites, which is a big chunky set of things. While that goes on, I just describe all the other stuff that's going to happen. So what we're going to do is just set up this machine so that it has all of the packages which Tezos requires for LIGO, for the Node client, for SmartPy, and for PyTezos. We're going to make a Tezos user, which we'll just use to do this stuff, so we're not doing it as root. And then we're going to install the Tezos clients, we're going to install LIGO, we're going to install PyTezos and SmartPy, and then we're going to clone a repo and install a contract onto the testnet if all goes well. Okay, cool. So let's become our Tezos user. Let's first of all, so the kindly people at Serical have made a lovely repo of all of the Tezos command line tools and the Tezos node. We're only going to install the node in this case, but this means that you can have a updated node which will update itself with every release, and this will make your life significantly easier. We're also going to install LIGO because we like to do this. So the easiest way to install LIGO is just to download the executable from the website and to put it into /user local bin. Whenever you need a new LIGO, you will just update this one. It's relatively straightforward. LIGO doesn't work so well for Mac users, I regret to inform you, and so you'll end up running it from Docker if you are a Mac person. That's just the way life is, I'm afraid. Let us see whether we can install PyTezos. Yeah, PyTezos seems to manage to install absolutely everything, not only from Tezos, but a whole chunk of stuff which is required for Ethereum as well. So it does take a while to install, and particularly if you're not on the world's fastest connection, but it gets there in the end and it installs pretty reliably. What I try and show you in a bit is that you can use PyTezos to interact with contracts in real time, which is really helpful, particularly when you're working on the testnet with a contract that you've written yourself and you wish to know how it behaves in the real world. So we hope this one goes relatively fast. Okay, very nice. Okay, so at this stage, we have a machine which is ready to run Tezos, and we have a Tezos client. Let's just make sure our home directory belongs to ourselves. Okay, so if we just type Tezos client, then we get loads of stuff coming out. The most important thing is to point the Tezos client at a node, which I'm going to get one from this list of testnet nodes. And I'm going to ask the node whether it's bootstrapped, which means whether it's caught up. And it's bootstrapped. Cool. While we were doing this presentation, I went to the testnets.xyz and I copied a faucet file to my clipboard. So I'm going to put that into a JSON file. And I'm going to activate myself a testnet account. And now I need to remember what the syntax is. Gate foobar. Dani, what am I doing wrong?
Okay, unrecognized command. There it is. Did you mean one of the following?
Okay, Dani, maybe we press on with the presentation while I try and work out why my technical have failed us at this moment.
Yeah. So we're going to be showing you some examples about compiling contract and deploying it. I'm going to skip these slides for now. Or just maybe mention that this is how we compile with LIGO. So you use the LIGO command line, and there's like compile contract, poll.mligo, which is like a smart contract we are compiling, and main is the function that we are compiling, and it will output the Michelson. So you can like pipe this into a .tz file, which is a Michelson file, and then use it to deploy. Then with LIGO, you need to compile the storage separately. So here you see a storage definition in LIGO language. And we are running LIGO compile storage, which looks at the contract itself and what its type is supposed to be, and takes this definition and compiles it into a Michelson data format, which you can see here, this pair thing. It essentially here we're setting an administrator address for a smart contract. When we have compiled the contract and the storage, we need to, of course, deploy it to the chain, and this can be like a mainnet or the mainnet or a testnet, or it could be a local flex data chain that we use for developer testing. And deploying a contract involves uploading the code itself to the chain, where we create an instance of it, that is. That's going to be callable, and we may transfer Tez to the contract at creation time, and we initialize the storage to something appropriate. Like here in the former example, you might want to set an administrator account who can, for example, with a token, mint new tokens. When we deploy a contract, it of course costs Tez. So we have to pay for the origination operation itself and for the on-chain storage that is used by the code and the initial storage of the contract. And we obtain a KT1 address and an identifier for the new contract, which is deterministic. It depends on the origination transaction itself. So we can know the smart contract address even before the operation had been baked. This is the way we can deploy a smart contract with Tezos client. So as you have seen, Tezos client has a really finicky interface. It uses these like supposedly human-friendly ways of writing commands, like kind of human languagey, like Tezos client originate contract pool transferring 0 Tez from Florence. Florence is an alias for an address that's that's installed in Tezos client. Running poll.tz. Poll.tz would be like the Michelson code. -- init, and here we add as the initial storage expression burn cap 0.424. That means 0.424 Tez is the maximum we are willing to burn to pay for storage. And then by running this, Tezos client will connect to the node and execute the contract origination transaction.
Okay, so my issue was that I was pointing at a mainnet node while attempting to activate a testnet test account. Having corrected that problem by pointing it at the correct node, I am now the proud owner of 103,588 testnet Tez and change. So the next thing that we're going to try to do is that we're going to compile a smart contract. So we clone this repo from Oxhead Alpha, which are probably the most battle tested and reliable of the smart contracts on the Tezos blockchain. They come in various shapes and sizes. We're going to use the one called multi-asset because it's the one that we have the best experiences with. Nice thing about the multi-asset NFT contract is that it behaves like pretty much whatever you want it to. If you make a token with an addition size of 1, it's an NFT. If you make one with several, it's a semi-fungible token. If you just make one thing in your contract, it can be a fungible token. So you can just do, if you apply one of these contracts, you have a whole ton of flexibility to decide what you want to do with it afterwards. So we're going to say LIGO compile contract, and we're going to point it at multi-asset LIGO source multi-asset fa2 multi-asset.mligo, and when we hit return, we get told entry point main does not exist because in this thing it's called entry point multi-asset main. And as you can see, we got a whole lot of lovely LIGO code out of the end. So we're going to put that in a file called contract.tz. We get these errors, these warnings. These are because the compilers become a lot better at telling you when you've got bad style than it used to be. So at some point, somebody will clear these up. The people who wrote these contracts were kind enough to give you an example storage, which we can see here at the bottom of this file. So we say have this thing, store multi-asset storage equals this. So what we're going to do is we're going to snip this out of the file. We're going to put it into a storage.mligo. And we're going to change some details to it. So the first thing to do is to put the admin to us. So we say, we ask our good friend Tezos client which accounts it knows about. And it knows about one. It knows about this one, which I made called foo, which is the one that we're going to use everything. So we're going to tell the contract that foo is the admin, and we're also going to tell it that it's not paused when it starts because we'd like to be able to interact with it. These other bits just say assets, it's an empty big map. Operators, it's an empty big map. Token total supply is an empty big map, and token metadata is an empty big map. So our contract has nothing but an admin at this moment. And so what we're going to do now is we are going to compile the storage. And I believe we have to do it like this. Yay, right, cool. So we can output that to storage.mligo. I think I just trashed my contract.mligo, so let's make that again. And now we can say this. Tezos client minus E, our node, originate contract foobar running contract.tz minus init cat storage dot tv. What did I call my stuff? And it will grind away, and assuming I got things right, originate contract new. Ah, yes, of course. We must always tell our contract that we wish to transfer a certain amount. So we say originate contract and its name, transferring 0 from foo, running contract tz, init. Origination simulation failed. Usually this is the burn cap. Anti-expression.
I think that might be something to do with the storage not being like maybe new lines or something weird. But I think we are like starting to run out of time, so maybe we should go on with the theory.
Okay, let's do it.
Okay.
I will relinquish the screen.
Okay, so we're going to skip SmartPy for now. There are very, very good online resources, and that we are linking to from the things in the GitHub repo that we mentioned. And also just Googling SmartPy is going to yield a lot of results. Let's talk about Taquito. So Taquito is the JavaScript SDK for Tezos. It is the most widely used Tezos SDK because, of course, if we want anything client-side in the browser, this is what we'll use. So it's the most tested and reliable SDK in the Tezos ecosystem. We really like it. It was written in TypeScript and has really wide-ranging functionality. So pretty much almost anything you can do with a Tezos node, you can do with Taquito. It supports various wallet and signer types. So you can define in-memory wallets, which can be like useful for server side, or you can integrate with the Beacon network. Now, Beacon is a standard in Tezos for connecting wallets. And it is a very flexible solution to writing distributed applications that support a wide range of Tezos wallets. Some notable wallets that might be important for onboarding and supporting people is there's Kukai. Now, Kukai is unique in that it permits users to create wallets and sign transactions using their social media logins. It does this in a secure, non-custodial way. So that means Google, Facebook, or Kukai won't be able to use and sign with your keys. So the key essentially gets generated deterministically on your computer. So it's relatively secure. By far not as secure as a hardware wallet, but still it's secure enough for a lot of use cases. And then there is Temple, which is a traditional in-browser wallet similar to MetaMask in the EVM ecosystem, which has hardware wallet support. So usually you want to support both of these, and if you use Beacon, then you get both out of the box for free. There's sample code in the repo for connecting with Beacon. And I do think that whenever you are developing a distributed application, it's a very good idea to use Beacon by default, because it gives you maintainability and compatibility with different wallets. And this is some Taquito code that I don't think we have really time to go through. PyTezos is the other popular SDK. It is written in Python, and it is relatively convenient. So because the Python has the Python REPL, it's really nice to work with. But there are still some stability and reliability issues with PyTezos, even though it's constantly being worked on. So we would say that if you're building something for production, Taquito is the tool of choice. But PyTezos can be really useful to just do something quickly and in an interactive manner. Indexers, we mentioned indexers before. So blockchain, the purpose of a blockchain node is to record transactions and not to be queryable or searchable. So querying blockchain nodes, especially in Tezos, is slow and resource intensive, and they are not very functionality rich in that regard. So for example, if you have a big map structure, which is which like it's similar to a map in Ethereum, where you have like any number of keys and you can lazy load or search values connected to them. So for example, a big map would store all the balances of a token for like all Tezos addresses who hold it. The Tezos node does not give you any way to enumerate all the keys in a big map. So that's where an indexer comes in. An indexer connects to a node, and it continually indexes the chain and builds this index, which allows you to run advanced queries on this data and gather like information that the node wouldn't give you. Like, for example, how many addresses are holding this token, who holds this token. And then, you know, an indexer, especially if you're self-hosting it, you can tell it to return you a million results, and it will just chug through and return it. There are two types of indexers in Tezos, and there are whole chain indexers, which are deployed publicly. So you can go to these websites and it's running, similar to like Etherscan, for example. But these are open source softwares that you can self-host as well. These index literally the whole chain from the beginning and give you access to all the smart contracts, all their storage, all operations, all balances. And sometimes this is overkill, especially if you want to self-host. So there are specialized indexers, which you start by specifying what you want it to index. So for example, you just want to index a specific token contract. And Capasa is a little tool that we have built in-house here in TZ Connect. It is a smart contract indexer. It can index one or multiple smart contracts and give a relational database as its output that you can query. A few words about token standards. So Tezos is not an EVM chain, which means it does not have ERC20 tokens. But there are Tezos token standards which are roughly equivalent. there is FA 1.2, which is roughly equivalent to ERC20, and FA 2, which is roughly equivalent to ERC 1155. So this is a multi-asset smart contract or token contract. It allows you to track multiple token types within a single smart contract. And since on-chain views were introduced recently to the Tezos protocol in a protocol upgrade, people are working on new token standards. So maybe FA 2.1 or FA 3, which would make use of this new protocol feature. Generally, there's very rarely a good reason to sit down and manually re-implement a token standard. It's a lot of work for not a whole lot of reward. There are existing implementations, some are better than others. Honestly, I would like to caution anyone against the SmartPy FA2 contract. It is non-compliant, which means that wallets and NFT marketplaces won't play nice with NFT contracts deployed with it. What we recommend is the Oxide Alpha FA2 multi-asset contract, very specifically. So the Oxide Alpha repo has multiple like FA2 types. We specifically recommend the multi-asset contract. I know this might not sound the best, but there is a set of really nice and quality smart token contracts in the works currently, which will be published soon, built in LIGO. And yeah, let me give the word back to John, because we'd like to wind down and maybe take some questions.
Sure, yeah, I will. I finally got my contract deployed, but I will not torment you by watching you watch along with the rest of this thing. So here are a list of developer resources. We have got all of this in our GitHub, along with sample code that you may find useful and a list of resources that we think are the best ones around. And now we welcome your questions.
Awesome. Thanks, guys. I think there's a few that have just come in the last few minutes. Aaron's question, Andrea's question, if you want to take those.
I like this question about the in-memory signer. Yeah, I mean, users' browsers are a bit of a hostile environment, not as much as they were in the 1990s when everybody had 5 rows of special search bars, but still there's a lot of code running in a browser from a lot of different places. And so you can't really be sure that the browser is super secure. On your server, you have much more control over what's going on. You may have it behind a firewall. We hope that it's fully up to date and patched. We hope it's not available for lots of people to log in. So on a server, you can take the calculated risk that you'll keep your key unencrypted in memory and signed there. You may choose to encrypt it on the disk so that if somebody comes across your machine, they cannot compromise the key. And for some specific uses where you're dealing with like a ton of value, then you may well want to use a ledger. The trouble is that security is the inverse of convenience. And so if you want your machine to run unattended, you will have to find a compromise that you're happy with, which gives you the ability to operate unattended while still not risking your keys more than you're comfortable with.
Yeah, like one thing that you can kind of do if you really want to play it super safe and secure is to have what you call a crypto enclave. A crypto enclave is a server, a physical server generally, that you have in a safe, like in a metal safe somewhere. And the only functionality is it exposes a signing. So you connect it to the machine that runs the Taquito code, and the only thing you let happen between the two is like sign requests. And that way, it's like an additional level of protection for your keys. But that's like kind of expensive and complicated to do. But like there are situations where it's warranted.
Yeah, we had one more question, which I think is a really good one. Our index is accessible by an on-chain contract. I mean, the blockchain is something of a walled garden. There are oracles which introduce off-chain data onto the blockchain. They introduce a set of problems to do with whether the data is authoritative and trustworthy, but this is their role. generally, if you're looking at the amount of data that requires an indexer, you're not going to be processing it in a contract anyway, because contracts are weak and slow and should be asked to do as little as possible. So yeah, business logic, as far as possible, can live off the blockchain.
Any standards, best practice for oracles? Very good
Yeah,
question.
yeah. So I mean, there's the Harbinger Oracle. There's another one around which are kind of de facto standards because they're out there putting values on the Tezos blockchain. I do not believe that there is a TZIP for oracles. I would love to be wrong, but I just think that there isn't yet.
Well, Dani and John, thank you so much for your time this afternoon and for a really rich and insightful presentation. So we very much appreciate it. Everyone will see you back next week. We're doing an ecosystem overview, which is a little bit more of a generalist one. In the meantime, everyone, thank you very much for coming this afternoon or this morning or this evening, wherever you are. Have a wonderful rest of the day, and we'll see you very soon. Thank you very much.
Thank you. Bye-bye.
Thanks, everyone. Bye.